Hmm. So, welcome back to live session 3. This session will be on this solid state welding basically. Um, so, mostly we will stick to the theoretical part here because there was not much scope to get some numericals in this ultrasonic welding and diffusion bonding. And, then you have this cold welding, pressure welding, those things. In this session, one numerical is there. We will do that in the last part. And during the session, what we will do, we will try to understand the bonding mechanism of solid state welding, different kind of welding techniques. So yeah, let us start. So in question one, it says that we need to select some incorrect pair of welding process and their bonding mechanism. Now, so to start with, why do you need to why do you need to join in solid state? Why don't you want some kind of fusion state as happen in arc welding or something like that? So solid state welding is easy or yes, it is easy to weld metals like aluminum and super alloys, those things. And in solid state welding, it can form some stronger and basically the main funda is here. Uh, Here you can form some intermetallic free welds, right? So there are different kinds of welding techniques as I mentioned. So you have this pressure welding, then you have this ultrasonic welding, diffusion welding, you can have this friction stir welding. Now, if we try to understand in terms of microstructure and surface condition of workpiece, what happens in workpiece, those are not completely flat in nature, right? You can see that in under microscopic scale there can be irregular surface. So you have irregular surfaces under microscopic scale, you know. So those surfaces can be covered with some oxides or some contaminant films. So they can be covered with oxides or some kind of contaminants, right? There can be some kind of compositional irregularities also. And what happen is like when you pressure them together, the two workpieces with those contaminants and oxide films and those irregular surfaces, those films can be broken up by this mechanical action, right? And those things can be break down the metal oxides. There can be some dissolution of the oxides into the matrix, right? And your local yield stress can exceed on that contact surface, and surface deformation happens. So those things are there, which is happening during this any kind of solid state welding. Now we need to basically here for this question, you need to match the followings of what mechanisms are there for different kinds of welding techniques. So we'll try to understand the very basic mechanisms of these welding techniques, and then we'll figure out which will be the correct answer. So first thing is explosive welding, right? So what happens in explosive welding? So here, here, if we try to draw some schematic of explosive welding, let us say this is my flyer material. You have your substrate over here, and you will have explosion over here. And this is my deformed zone, right? This is what happened in explosive welding. So this kind of solid state joining process that uses some explosive force to create that metallurgical bond between two metal components. And here your time duration is so small. The impact duration is so small, so it can be considered as kind of adiabatic heat rise, right? Now, what are some common applications of explosive welding? So, if you think of some application here, so people normally use this cladding of steel component with some kind of corrosion resistant material. During that time, you can use this explosive welding. Now, during explosion on the flyer plate, so a high pressure pulse is getting generated, right? And this pulse basically is propelling the flyer plate at a very high velocity. And so this is kind of some kind of jet is jet is the product of that collision, and that jet formation allows two pure metal surfaces to join under some extremely high pressure. So whenever you are uh, doing some deformation in very short period of time, deformation in very short period of time, during that time strain rate plays a very important role, right? Your stress will be function of both strain rate and temperature. है ना? Now here the occurrence of welding depends on piece of metal plate that collides at what angle with the parent metal plate. So this also depending on the angle of the collision. Now, if we try to understand the process geometry, here some kind of parallel plate bonding is used for large plates. Your flyer plate velocity can range from something like how much? 200 to 600 meter per second. And at the collision point, velocity is very high. So it can range from something like 1000 to 3000 meter per second at the collision point, the velocity, the final velocity. And you can vary your collision angle from in between 5 to 20 degree. These are some general process parameters people use in explosive welding. And here the impact must be sufficiently high to cause the colliding metal surface to flow some like hydrodynamic there can be some hydrodynamic flow when they intimately contact each other, right? Now here what should be the mechanism of this explosive welding? Can anyone try to guess? Oh, you need to select the incorrect pair of welding process. So before that, I think I should explain a little bit of other techniques also. So here we have this explosive welding, then you have this ultrasonic. What happens in ultrasonic? Hmm, what happens in ultrasonic welding? So if you think of this ultrasonic welding, I'm rubbing this part. So if you're thinking of this ultrasonic welding, so this is kind of some kind of coalescence is happening over there, and this is produced at the faying surfaces. What is the source of ultrasonic welding? The high frequency vibrator energy, right? So in ultrasonic welding, high frequency vibration is the source of joining. Now here you need to hold the workpiece together under some moderately low static pressure. Now it produces a weld by some oscillating shear force. So these are some terms which I am using here. So if this is your horn like this, let's say this is my horn and this will be my workpiece to be joined, and here you have your anvil like this, and this will be vibrating in the planar direction, right? So it will create some kind of perforation over this sheet metal and also at the interface. So because of this deformation and basically it is kind of interlocking of two different metals altogether, and that is how the ultrasonic welding is happening. Now I will come later with these different types of ultrasonic welding. So what are the different kinds of ultrasonic welding? There are two kinds of ultrasonic welding. One is this wedge rate system. What is another? Anyone? What is the other kind of ultrasonic welding system? One is this wedge rate system. The other is called
Sir, lateral drive.
lateral drive. Right. The other one is lateral drive. Now, if you see in wedge rate system, this is a kind of here accurate control on the parameter is not possible due to its bending mode. So if we try to draw this schematic, how does it look like? Here we will have some kind of mass over here, and this is the complete mass, and this is my workpiece to be joined, and here you can have this anvil. So this is my anvil, and how is the sonotrode vibrating? So this is my transducer, And here you have this sonotron tip, you know, and vibration is happening like this. So this is kind of bending mode operation because of this long mass over there. And here the mechanical vibration is getting transferred to the workpiece. Now here the anvil also sometimes can act as a vibrating part, and yeah, the anvil also can sometimes act as a vibrating part. And when these kind of system used in ultrasonic welding, this is mostly used in sheets with large thicknesses. So wedge-rich system is mostly used in large thickness parts. Correct? Now, what will be happening in lateral drive system? So, in lateral drive, I'm rubbing this part. So, in lateral drive, again, you have some transducer, then you can have some, so it's kind of a power supply over here. And through this power supply, you are powering up your sonotron. So, let's say this is my sonotron tip. And here you can apply some kind of damping over here, and the vibration is in the planar direction, like happen in Vajri system also. And you have this welding over this two workpiece, and at the bottom you can have this anvil over here also. Now here this lateral dive system allows the welding parameters to be measured by a transducer, and it gives good results for thin specimens. So mostly people use this lateral drive system for thin specimens, right? So yeah, what is the mechanism of this ultrasonic welding? Uh, in short term, what we can say. So as I was saying, there will be some sleep and deformation. I hope you are familiar with this sleep and twinning mechanism. I'm not going into that detail. So it's basically sleeping is happening. You are basically moving the dislocation defect, and so there are two kinds of dislocation. I hope you know, age and screw dislocation. So you are dislocating the workpiece, you are deforming them, sleep is happening, interfacial sleep is happening, and plastic deformation is happening, right? And here also the temperature is getting influenced by the power of that sonotrope, by the clamping force, and also some uh, thermal properties of the material like conductivity, specific heat, uh, even density also. So your thermal diffusivity, uh, are you familiar with this thermal diffusivity term? I hope you are familiar with this thing. Alpha equal to K by rho Cp, right? Depending on that, your thermal diffusion length will vary. So, yeah, that localized plastic deformation is happening over here. Now, what are the advantages of ultrasonic welding? So, here, hardly any heat is applying. Hardly any heat is applying here. So, your all the things over here is forming because of deformation. So no heat is applied and no melting is happening over there. So it permits the welding of, as I was saying, for this reed system for thick sections and this lateral drive for thin section. You know, and here pressure also used are lower. These welding times are shorter, and the thickness of deformed regions are thinner than the other welding techniques like cold welding one is there, cold welding. Here I will mention that also. And what are the limitations of ultrasonic welding? So if you see the thickness of the component adjacent to the sonotrode tip, that must not exceed relatively thin gauges because of that power limitation of that equipment. And always the main disadvantage of ultrasonic is like the process is just a minute. Uh, so the process is limited to lap joints only in ultrasonic welding. The process is limited to lap joints only. Now, what is happening during cold welding? So there is something called cold welding. Cold welding is also is kind of a solid state welding process in which again you are applying some pressure where the pressure is used at room temperature. So here also you are doing everything at room temperature again to produce some coalescence and metals with substantial deformation can happen at the weld. But here the main advantage here is both butt and lap joints can be cold welded over here. Now, what are the process steps of cold welding? What are the process steps of cold welding? So first for every welding you first clean the workpiece, right? So first thing first, you need to clean the workpiece, and then a short section of the part is getting sheared. Shearing of a short section of a part. Now, sometimes the parts are clamped in a die with some initial extension, like if these are your two parts to be joined, and you can have die like this, right? And you are applying pressure over here, like this, right? So this will be joined all together. Now, it is kind of a forging is happening over here. So we call it forging force is applying. Now, now in terms of characteristics of cold welding, here the metals must be ductile without some excessive work hardening. Otherwise, at room temperature, you cannot do joining, right? So, if you are joining some hard metal at room temperature, you cannot deform only by pressure. Like happen in friction stir welding, you basically rub the workpiece against the tool. You have to have rise the temperature of the material. Otherwise, it cannot be soft, it cannot be deformed. That's why in cold welding, as this is happening in the room temperature, mostly people use this ductile material without some excessive work hardening happening. Total absence of heating source. You can join dissimilar metals also, but the most important in cold welding thing is surface preparation. You have to prepare your surface very carefully, right? Now let us find out which one will be the correct answer over here. We need to select the incorrect pair of the welding process and their bonding mechanism. Which one will be the incorrect? So in explosive welding, there can be localized melting. Mm, in friction stir welding, also there can be localized melting. So localized melting mainly occurs in these techniques. In explosive welding, then friction stir welding or friction welding, then your ultrasonic welding. This is also some frictional heat is getting generated over here, right? Here localized melting happening. And what is this diffusion based process? So here, this is my incorrect pair. So here diffusion is kind of thermally activated process related to some material properties, of course. Then you can have some kind of. Are you familiar with this concept of recovery, recrystallization, those things? Yes, no, anyone?
Yes.
Right. So recrystallization is also a kind of mechanism in solid state welding. So here basically some kind of intimate contact between two mating surface uh, is happening over there by means of this recrystallization process through migration of grain boundary. There is another mechanism called adhesion also. What is adhesion? So adhesion is like some kind of atomic attraction. So adhesion is some kind of atomic attraction between two atoms that reaches a maximum at some interatomic distance. So um, there are some relationship between the free energy and the interatomic distance. Do you remember that? This is kind of atomic attraction happening over there between two atoms, and it reaches uh, some maximum at a specific interatomic distance. And here also the surface preparation. For every solid state welding, you have to have prepared the surface very carefully. You need to break those oxide films, otherwise joining cannot happen at at very low temperature. So surface preparation is always very important for solid state welding. Okay, I have talked I have talked about this all these mechanisms and different welding techniques over there. Now, in second question, it says, in which solid state welding bonding mechanism grain boundary migration occurs? In which mechanism grain boundary? I just mentioned it. Can you
Sir,
tell me the answer
recrystallization.
again? Mm-hmm.
Recrystallization.
Right. So, in recrystallization. grain boundary migration occurs. Now, what about, I have talked about this diffusion, I have talked about this recrystallization. There are two more mechanisms, which is this interfacial morphology and interfacial reaction. So, in interfacial reaction, it is kind of this reaction of these oxide films within the weld metals itself. So, in interfacial reaction, this is the reaction of oxide films within the weld metals, right? What is happening is it is kind of the oxide is getting solutionized. So here, solubility of oxides at interface is very important over here for interfacial reaction, right? Now, whenever whenever your oxides is getting solutionized into that region, into that well region, so your two metals will contact each other, right? Will come together and they will react in between themselves and they will form something called intermetallics. So intermetallics are some kind of phase formation. So this is kind of alloying formation. Let's say you are joining some aluminium to copper, and if you see the phase diagram of aluminium and copper, there will be phases like Al2Cu, AlCu, Al4Cu9. Those are the phases over some defined temperature at some defined composition of aluminum and copper. So these we call intermetallics. So your intermetallics always are harmful to the joint strength. But in some sense, you need some amount of intermetallics to have some sort of hardness over the region. It is not like there should be some balance in between your hardness and formability and ductility and strain. Those things are there. It should not be that much brittle. It should not be that much ductile. You should balance to get the best end product, right? So this was my interfacial reaction, and then you have this interfacial morphology. So what is there in interfacial morphology mechanism? What is there in interface morphology mechanism? And in which welding technique can I see this kind of morphological change over the interface? So in explosive welding, this is kind of unique characteristic that interfacial morphology. Uh, in explosive welding, sometime in ultrasonic welding also. So initially this was a planar interface, right? Initially this was a planar interface. Now in explosive welding, because of this very high velocity, what will happen? It will form some kind of waviness over the region. And if this is becoming some wavy in nature, what is happening? The area percentage, the contact area is getting increased, right? This is getting some kind of interlocking over here, is it not? So your contact area is getting increased. This is mostly seen in explosive welding. In ultrasonic welding, also in some sense, this can occur because you have this sonotropy, right? This is having some kind of profile like this, and if it apply a pressure in this direction and vibration, so your joining, whatever joining will be there, there will be this kind of perforation over there. This also depends on this interlocking of two plane surfaces. And here, the amount of waviness, what does it depend upon in explosive welding? So it depends upon, I have already mentioned those process parameters for explosive welding. You have this collision angle, I know. So you have this collision angle. What else? You have your velocity of the flyer plate relative to the collision point. Correct? So, yeah, we have already talked about this question. In recrystallization mechanism, the grain boundary migration occurs. Okay. What about the third question? This also I have already mentioned. Want to give it a try?
Sir, ductility.
Right, right. So, what I told during cold welding, you have these two workpieces. You can apply pressure from these two sides. You can have this die over here. Let's say this is my die. This is my die, and the pressure is used at the room temperature only. Correct? Now, how will it look like? So it will form some kind of joint over here, and these are the dies over there. Hmm.
Sir, the force applied is only axial or some radial force will be also there.
So always you are applying pressure, of course, in axial direction. Otherwise, always the pressure direction should be normal to the interface. Anytime, any kind of welding process. Just a minute, sorry. Hmm. Is it visible?
Yes, sir.
Yes, sir.
Hmm. So yeah, so any kind of welding process, you apply the pressure always normal to the interface, but In terms of reaction forces, always there can be some kind of forces in lateral direction. So in friction stir welding, so I'm explaining in terms of friction stir welding. So this was your tool, right? Let's say this is my tool. This is having a pin. You rotate the tool, you apply the plunge in this direction, the downward direction. What is the interface? This is my interface, which is normal to this downward plunge direction, right? But always you can feel some reaction force in lateral direction. Always you can have pressure in. So this is a vector. It's not like that you will get force in z direction only. The reaction forces are there in x and y also. Okay.
Okay, sir.
Hmm. Okay. So here for cold welding process, the material should have good ductility. Otherwise, as we are doing the joining in room temperature, otherwise for other techniques, you always need some heating source. And if you are joining some hard metal, you have to soften them. Otherwise, you cannot only by pressure you cannot deform the material. You have to increase the temperature, soften them. You need to reach to some viscoplastic state, and yeah, those things are there. Those strain hardening model. Correct. So here it says, what is it asking? In which of the following welding process no heat is applied for the welding? So it basically asks, uh, not any kind of heat source is used, maybe external heat source.
Sir, option C?
It's B.
No, option B. C. I'm telling option
Yes,
C, sir.
Sir,
it should be
ultrasonic and cold welding.
ultrasonic and
In
cold welding, right?
in both cases, we do not apply any external
Correct.
heat.
Now, what is happening in diffusion bonding? We have a lot of discussion regarding this ultrasonic, cold, and explosive welding. What is happening during diffusion bonding? This is also a solid state welding process, of course. And what is happening over there? Same mechanism for diffusion bonding also. Here also you have this coalescence of these two faying surfaces. Now, let's say you have two metals. You are applying pressure, right? So you have this metal A. I'm doing diffusion bonding of two different metals. You're applying pressure, and also you will have some. So this is in generally done in vacuum furnace. So you have a heating source. correct? Now, here the process does not involve any kind of macroscopic deformation, or you do not have any kind of relative motion of these two workpieces. These are fixed altogether, right? And you keep it in vacuum furnace. That's why diffusion bonding always takes a long time. Very long time is required for diffusion bonding to happen in solid state. Now, people have used different kinds of filler metals also, some solid filler metals that may or may not be inserted between those fairing surfaces. Uh, so if we try to understand the mechanism, what is happening over diffusion bonding regions, you have these in the first stage. In the first stage, what is happening? The asperities or the surface irregularities, whatever was there, those come into contact, right? Then you will have some kind of interfacial boundary formation. You can have some here also, you can have some grain boundary migration, recrystallization, those things. Then you will have this volume diffusion, right? Now, how does this volume diffusion happening? So there is one thing is called grain boundary diffusion. So what is happening over there is like this. So initially, let's say we are having surface irregularities like this, okay? And then this is my first stage. In the second stage, it will form this interfacial boundary over here, but it can form these voids will be over there like this. It will always take some time. And then what is happening, this grain boundary migration, those sophisticated terms are over there. This grain boundary diffusion, volume diffusion, and grain boundary migration. What is happening over there? During the time domain, the material from this boundary, this grain boundary, they move towards this like this, and they try to fill up the voids. So this we call this pore elimination also. This is a time consuming process, of course. Now, what are the factors which influence this diffusion welding? What are the factors which influence this diffusion welding? I once talked about this thermal diffusion length. That is one factor. So let's say X is my thermal diffusion length. That is proportional to root over of d into t. What is d? D is the diffusion coefficient. You're also familiar with this Fick's first law of diffusion. D is the diffusion coefficient. And what is the time? This time of diffusion. right? And how diffusion coefficient is varying with temperature. So there is one relation of T equal to T naught into T to the power minus Q by KT, where Q is your activation energy, T is your absolute temperature. What is K? What is K?
Boltzmann constant.
Correct. K is Boltzmann constant. T naught is diffusion constant. This is my diffusion coefficient. You can find out the diffusion coefficient at specific temperature, depending on your temperature. So people generally use some molecular dynamic simulation to understand how how the metal atoms are diffusing into each other. Let's say we're joining some aluminum and copper. So those two metal atoms can have different atomic radius, of course, right? Aluminum is having some atomic radius different from that copper. So mostly copper is having smaller radius. So copper can diffuse into aluminum very easily. So people can do some simulation, some molecular dynamic simulation. Like how fast copper is diffusing into aluminum, at what rate, to which depth, what will be the diffusion coefficient at that temperature. So those things are there to analyze uh, in terms of diffusion happening at some region. Yeah. Okay. Hmm. What is this question? Which of the following material is used for sonotron and anvil in the ultrasonic welding process to weld high strength metals? Okay, before that, can you tell me what are the process parameters in a ultrasonic welding? What are different process parameters? So you're vibrating a sonotrode over a region uh, for a specific amount of time at some specific amount. You are applying some specific amount of pressure over that region. So what can be the process parameters? So you can have this clamping force, right? You can have welding time. What else you can have? Of course, we'll have some amount of frequency of the vibration, frequency, amplitude of the vibrator, right? These are some process parameters in ultrasonic welding. Now, in terms of this sonotrode tip and anvil material, what are the what are the materials you can use? You can use this high speed tool steel. One thing is high speed tool steel. When you use this high speed tool steel, people generally use this kind of material when they're trying to weld some soft metals like aluminum. Aluminum is very soft, very ductile. Copper is a little bit hard than aluminum, but this is also malleable in nature. You can use some low carbon steel also, right? And the sonotro teeth and anvil material can be used some hardenable nickel based alloys, which are very hard in nature. This kind of material is used for hardened high strength metals and alloys. Okay, so D is the correct option, right? Any question? Hmm. Now this is in terms of this friction stir welding. Anyone here familiar with this friction stir welding, or have you ever come across this technique or any kind of experience in friction stir welding? Anyone? Yes, no. So if you see friction stir welding, uh, this was initially invented for aluminum alloys. So when this was invented first, it was used for aluminum alloys only. Nowadays, people use for dissimilar metals also, joining of dissimilar metals, joining of some high strength, high temperature resistant like nickel based alloys. Those things are coming recently in friction stir welding. This is, you can say, a green technology due to its energy efficiency, due to its environment friendliness, right? So here what do you have? You have some specially designed non-consumable rotating tool, right? So it can be with pin or without pin. So if you thinking of this tool material, this is what we call it pin, and this is what we call it shoulder. There are two regions of a tool, which is pin and shoulder, right? And this is basically rotating and plunging against the workpiece material. So here the rotating tool is inserted into the batting edges of this workpiece. Of course, will be rigidly clamped, and this during welding this can be traversed in this direction. You know, so this is how it happens. Now there is of course inside mechanism is complex in nature. So there are few concepts of advancing side, retreating side. So there are few concepts of what is advancing side. So advancing side we call it the side which has similar sense of tool rotation and the traverse direction. So let's say this is the top view, right? And this is the direction of rotation, and this is traversing in this direction. So let's say this is my workpiece material. So which side is my advancing side? If this is rotating in this direction and the traverse direction is this, so this will be my advancing side, and the other side we call it retreating, right? Which has the opposite sense of tool rotation and the traverse direction. I know. Now, in different phases of time, let us try to understand what is happening in friction stir welding in different phases of time. So initially, this was my workpiece, and this is my tool, right? And it is touching the workpiece. And then we are giving a plunge. So during the plunge, this is my workpiece, this is my tool. This will come a little bit below, and this is getting plunged. Understood? This is what we call it plunging. And then you provide more plunge, and the tool is continuously rotating over there. You touch the shoulder over here and provide a specific amount of plunge depth. It can be equal to the pin depth or it cannot be. Okay. So here let us say we are applying the complete plunge depth of the pin, and we are applying some amount of initial dwell phase. So first you touch the workpiece, you apply the plunge, you insert the pin into the workpiece, then you provide some plunge depth. It is continuously rotating over here, and then you apply some amount of dwell time over that period. And when there is sufficient amount of viscoplastic deformation, it is coming into the softened state. Uh, this is totally the material mixing is taking place. During that time, you start the traverse period. So this was my workpiece, and initially it was here. Then let's say this is coming into this region. So this is my traverse state, right? So how does this tool contact surface is varying over the region? So initially, let's say this was my pin bottom surface, okay? This was my pin bottom surface. And then the contact area is getting increased up to what? Up to the side surface also. Initially, this was the bottom surface only touching the workpiece. When you are applying plunge, your side surface is also getting into contact with the workpiece, and the contact area is getting increased, and then finally you are increasing up to some shoulder surface, right? So let's say this is A region, this is B, and this is C. So what is A? A is pin bottom surface. What is B? B is pin side surface. And what is C? This is shoulder surface, right? This is how the tool contact area is getting increased during the complete process. And then you have this traverse. when the complete shoulder is getting into contact of that workpiece. And then again, when you are retracting the tool, the contact area is getting decreased. That's how it works. Any question?
No, sir.
Sir, the pin will wear out or not in this process?
It depends. It depends. So it depends on the tool configuration. It depends on the tool material itself. So for hard material, we generally use some tungsten carbide metal, so which can oxidize very easily. So sometimes it happens tool is getting broken because of that axial thrust it is applying over the workpiece. It can happen. It depends on the fabrication process also. Generally, you can what tool materials we used? We use some, let's say, 13 tool steel. You can use tungsten carbide. You can use tungsten carbide, cobalt alloy. So these two metals are used mostly for welding of hard metals. Hard in the sense which can apply a resistive force very easily, like steel. So aluminium can deform very easily, right? So for aluminium, we can use this tool steel material. Now this tungsten carbide can break. It depends on that this powder metallurgy process. So people use this powder metallurgy to fabricate this kind of, not this tool steel. This can be turned this tungsten carbide and tungsten carbide cobalt metal. These are coming through this powder metallurgy process.
Sir, yeah, one more question is this tool pin. It is rotating against the transverse force of the workpiece. So, is there any case like such that material removal is there? It looks like a machining process.
Mm, can you come again? I was not completely into that. Just one more
Uh,
time.
Sir, actually, this process looks like a machining process. So, during this welding process, is there any case of material removal? Like the tool is rotating and the workpiece is moving transverse in a transverse direction.
This
Is
is
there
not
any?
a material removal process. So when you are applying pressure, so basically you are applying pressure, right?
Yes,
When you are applying pressure, the material is getting deformed. It is not kind of a removal process. The material is getting deformed. The material is because of that pressure and temperature which is originating from that due to this friction. So basically rubbing action is happening over here, right? So friction all over the region where this shoulder and pin is getting into contact with the workpiece, friction is there. So frictional heat is getting generated, and that frictional heat is converting into this plastic deformation, and it is reaching, the material is reaching into some viscoplastic state, right? Above some recrystallization temperature maybe. And at that region, material is very easy to flow, you know?
yes.
So at viscoplastic state,
Okay, sir. Thank you.
hmm. So this is not a kind of machining process as such, but yes, you can think of some kind of flash formation is always happens over there. So we call it flash formation. If you uh, watch some video of friction stir welding, you can get some clear view. Hmm. So in terms of this process or different working regions in friction stir welding, we generally divide in five different working zones. One is this preheated region, then you have this initial deformation region. Just a minute, can I have some water, please? So, um, yeah, one was this preheat, then you have this initial deformation region, then you have this, we call it extrusion region, and then you have this forging region, and finally the post heat or cool down region. So this is how we differentiate the working regions in practice. So what are happening at those locations? I'm not going into schematic because this is a big schematic I need to draw again and again. So let us try to understand verbally. So what is happening in preheat zone? So preheat zone is basically ahead of the pin. So uh, if you have this shoulder, and if you have this pin over here, and let's say I'm drawing the 2D over here. So the most left will be this preheat zone. Then here it will be this initial deformation zone. In the vicinity of the tool, there will be extrusion zone and forging zone. And finally, again, here you will have this post-heat zone. Okay. So what is happening in preheat zone? Here the temperature is basically rising due to the frictional heating of the rotating tool and uh, what I was mentioning uh, earlier. So here some kind of adiabatic heating is taking place because of the deformation of the material, right? Now, as the tool moves forward, this initial deformation zone forms during the traverse one, right? So material is getting heated to above some critical temperature, maybe the recrystallization temperature for that material, and your magnitude of the stress that exceeds the critical flow stress. So you're familiar with this Tresca, von Mises silk criteria, right? So your magnitude of stress is exceeding the critical flow stress, which is your yield stress of the material. That is resulting in the material flow. What I was explaining, like it is reaching in its viscoplastic state, right? Now, the material in this zone is forced both upwards into the shoulder and downwards into the extrusion unit. So, um, it is like this is rotating like this, right? This is rotating like this. And what is happening in terms of material movement? Some upward and downward thing is happening over there. So, in that region, the tool is forcing the material to go to the downward direction, and the subsidiary regions are basically coming upwards to fill up that cavity, something like that, right? And what is happening behind this forging zone, this post heat and cooling zone? That is where the material gets cooled, right? Under some there can be this passive cooling, there can be this forced cooling condition. Um, as you know from this heat treatment, there can be air cooling, there can be uh, water cooling, water quenching. Those things are there. Any question from the mechanism per se? Okay, so for this
Sir,
question,
tell me
uh,
once again, please, where the material is moving upward to downward rotation.
mhm.
I cannot understand this mechanism. Please repeat this.
So ideally, for these things to understand, you need to do some scanning electron microscopy actually. Uh, so theoretically, what is happening is like there are two different regions, right? This extrusion region and the forging region. So in extrusion zone, uh, the material flows around the pin. So if you are having this tool rotating continuously, it is rotating continuously, like so. What will happening with the material? This will also flow around the pin from the front to rear. So if you are thinking of in terms of 3D, right?
Yes, sir.
So when the material is, let's say, here my material initially it was there, and the material is getting flown over here. Okay, now here is my material. Initially it was here. So here some kind of cavity will form, right?
Yes, sir.
So when there is some kind of cavity formation is there, and initially there is also some material over here, this is coming into this region. So it is kind of material mixing taking place continuously, and it is like it is upward, backward, and all over the regions material is getting stirred due to this tool rotation. So the material from the front of the tool that is forced into the cavity that is left behind by that forward moving pin. Am I able to explain?
Yes, sir. Thank you, sir.
Okay. Okay. So which one is not related to the friction stir welding process? Flyer. So flyer is related to which process? Flyer is related to which process?
Sir, thermite welding.
Mm-hmm. I can't hear you. Which process? I told na this flyer plate that is moving at a very high velocity. The collision is happening with a plate. where this is used, this flyer plate. We use it in explosive welding. Now, what are different process parameters in friction stir welding? So these are some very quick question answer round kind of thing. So before that, I will just discuss regarding this process parameters of friction stir welding. So what are different process parameters in friction stir welding? So you have this tool RPM, right? So you can have this clockwise or counterclockwise direction. And because of that tool rotation, that is resulting in that, as I was saying, stirring and mixing of the material around the pin, right? So what do you think, which will generate higher temperature, higher tool RPM or lower tool RPM? If it is all based on friction,
Higher total RPM.
of course, so higher tool rotation will generate the higher temperature, right? Due to this frictional heating. Now, what else? What else process parameters do we have? You have this tool traverse speed. You have tool RPM. You have tool traverse speed. Now, in tool traverse speed, let us say you have high welding speed. One is low welding speed, which will provide you higher temperature.
Sir, low welding speed.
This will provide you higher temperature.
Low welding speed.
These are the basic sense, right? Everyone agreed, right? Everyone agreed that low welding speed will provide you higher temperature.
Yes.
Yes. Okay. So there are other parameter, some specific process parameter regarding this friction stir welding. We call it tool tilt angle. You can tilt the tool also. So this suitable tilt angle ensures some effective holding of material by the shoulder while you are moving the material from the front to back. So you can tilt the tool like this when you are traversing along the workpiece material. Okay. Then what else do you have? You have the plunge depth also. You have the plunge depth also. This is important for producing some smooth weld surface. You can have shallow plunge depth, you can have deep plunge depth. So in what happens in shallow plunge depth? Here the shoulder, this is my shoulder, right? This interface is the shoulder interface. In shallow plunge depth, shoulder doesn't touch or contact the workpiece surface, right? Thus, it cannot move the material from the front to back of the pin, producing welds with some surface grooves or tunnel. So, because of that material mixing through the pin, sometimes defects like tunnel defects can form. We call it tunnel defect. If there is improper mixing of materials or improper stirring of the material around the pin. So, of course, if you have a shallow plunge depth, you cannot move the material from the front to back of the pin, right? And then there is deep plunge depth. When your shoulder plunges into the workpiece and you are applying the complete pin you are inserting into the workpiece, and the pin length is the plunge depth. And what are the disadvantages of deep plunge depth? They produces excessive flash, as I was mentioning, flash formation over there. This is kind of wastage of material. It produces excessive flash, and sometimes it can form some concave weld because of high amount of axial thrust. If you are applying more plunge, you are producing more thrust over the workpiece, right? So that leads to local thinning of the sheet metal you want to join. So deep plunge depth leads to concave weld leads to local thinning of metal sheet. Okay, there are a lot more things in friction stir welding I can explain, but I will skip in the short period of time. There are different kinds of tool materials. People are doing research in tool geometry also for proper mixing, proper studying of the material. You can analyze the material flow, how is the pattern of the material flow around the pin, how is the material is getting mixed. Then you have this um, how your axial thrust load is getting varied during this plunging, dwelling, and traverse stage. Then there is heat generation. I have one numerical on this heat generation that we will cover. Okay, just go through this
Sir,
seven eight.
can I ask a question?
Sure.
Sir, up to what thickness we can use this friction stir welding? Means
So
up to metals of
usually, uh-huh.
material sheets of what thickness we can weld by this?
Mhm. So usually people have used thickness of up to, I have seen thickness of up to 5 mm people have used. But yes, again, as this is a heavy duty machine, friction stir welding is a heavy duty operation because this is generating some axial thrust over there. Uh, more the thickness, more the hardness, more will be the axial thrust, more will be the tool wear.
Yes, sir. Sir, if we like the tilt angle, if the tilt angle is higher, then what are the advantages?
Sorry.
Sir, if the tool tip is kept an angle,
Mm-hmm,
like in that case of tilt angle,
mm-hmm,
at tool tilt angle, if the
mm-hmm.
angle is more, then what will be the advantages?
So it should be kept in optimum condition. So people use 2 to 3 degree. It should not be
Okay,
very low. It should not be very high. So if it is very
okay,
low, uh, the material doesn't get stable in that region. So mixing will not take place very easily. And if it is very high, it will like a, how should I say? Uh, it will be like
okay.
a, mm, it will penetrate basically. It will, if it is too high, this angle, if it is too high, this will penetrate the workpiece material and more material will getting into upward. So there should be some optimum condition to say. So we normally use, I'm also working in this region, in this domain. So we normally use 2 to 3 degree of tool tilt angle.
Okay, sir. Thank you.
Mhm. Okay, so just go through these questions and tell me the answers. I have talked a lot about different kinds of techniques and their mechanisms. So you need to identify the correct pair of welding process and terms associated with them. One more thing. Electromagnetic pulse welding I have not touched upon. So just let me give some time for this electromagnetic pulse welding. So what is happening in electromagnetic pulse welding? What is the principle of operation for electromagnetic pulse? So it follows simply an Ampere's law, right? So the current carrying conductors, when placed nearby, they exert some force on each other. The magnetic field is getting created. So there are some equation like F equal to mu naught by 2 pi t into 1 I2. That's how you can calculate the force between this infinitely long parallel conductor. What is mu naught? Mu naught is the permeability, right? What is D? Is the distance between conductors, correct? And I1, I2 is the current flow. And then you are generating some magnetic field through Lorentz force. These things are familiar, I hope. What is the Lorentz force? J into B. So J is your current density and B is your magnetic force, right? Now, in electromagnetic pulse welding, uh, you use some kind of capacitor bank to store some energy, which is charged through a DC power supply. You use some DC power supply to charge those capacitor banks as an energy source, and then that energy is discharged through the some kind of work coil, uh, and then the welding time is very less. So it is something like 50 microsecond or something like that, in between 30 to 50 microsecond. The welding time is very less here. Uh, yeah, who is joining now? So in electromagnetic pulse welding, what is happening is like here the induced electromotive force and the corresponding eddy current in the worksheets, those oppose their cause, right? So the induced eddy currents that depend on the material properties, like what are the properties it can depend upon? Uh, it can depend on your conductivity of the material. It can depend upon the permeability of the material, right? And finally, what is happening? Like the worksheets are repelled away from the coil towards each other, and they create an impact. And due to the Lorentz force, they last for a few microseconds. And due to that interaction between those induced eddy currents and magnetic fields, that's how it works in electromagnetic welding. I'm not going into the detail of this process parameters. There are, of course, all applications, specific applications for electromagnetic pulse welding. Anyhow, can we identify the correct pair of welding processes here? Hmm? So
Sir,
this I can
option
understand.
A.
This is A, option A.
Yeah, yeah.
So option A is 1, 3, and 4. It's possible. Yes, this is true. Uh, this is not true. This is false because ultrasonic welding is a neutron. Friction stir welding is this is true. 1, 3. Cold welding forging force. Yes, this is also true. And this is also false because eddy current is for, as I was saying, electromagnetic pulse welding, right? So yes, you are right. A is correct. Next question. In the diffusion bonding process, joining is achieved by in the diffusion bonding process, joining is achieved by application of you need to fill in the blank at some what temperature. What it should be.
Sir, answer is option C. Pressure
Right,
and
right,
elevated temperature.
right. Option C is correct. So we have to have some elevated temperature. Uh, and basically you're applying pressure over there. I hope everyone is agreed, right? Just tell me if I'm not agreed with the answer. Should I move to the next question? Due to which reasons the friction stir welding process can be referred as green technology? Yeah, yeah. Okay. It's energy efficient compared to the other welding process. This is true. It does not produce any kind of gases during the welding process. Yes, this is also true. Is this is so much pure, I can tell you. There is no kind of melting is happening over there. Like in fusion welding, there are a lot of porosity occurs because of this gas entrapment, air entrapment. Um, in arc welding, you need to use some, what should I say, some uh, argon gas chamber maybe to protect the weld pool. Those things are not there in friction stir welding. So one is true, two is true. Mainly for these two reasons, this is termed as a green technology actually. So here is your correct answer. Select the correct set of process parameter for the electromagnetic pulse welding process. Inductance of the circuit, true or false?
True, sir.
This is true. Tool geometry, there is no tool, of course. What about clamping force? Should there be any clamping force? No. The frequency, yes. And the voltage. So these are some of the process parameters we use for electromagnetic pulse welding. Any question till now? We have the last numerical. Great. We'll move to the last question then. So we have a FSW tool which is having some shoulder diameter of 16 mm. Let's say you have this shoulder dia of 16 mm and you have pin dia of 6 mm. So I have taken this random values now. So don't be confused with the practical application. And then I am saying that the tool is applying a pressure of 50 megapascal. Pressure is 50 megapascal. You have a coefficient of friction as 0.2 and I am saying that you assume a sliding friction. So there are what are two different kinds of friction at contact interface? One is sliding friction, another is anyone? One is sliding friction. Have you heard of this sticking friction? Yes, no? Okay, great. So your frictional coefficient is 0.2, and you need to find out what is the total heat is getting generated at the tool material interface. And you consider the tool RPM, AN is equal to 1000 RPM. Okay, what can we say about this heat flux getting generated over a small region, dq? So this is basically the power, right? E equal to F into V, force into velocity. Is it not? So in arc welding also, you know your voltage ampere characteristic, you know the power. So that power is getting converted into the heat flux, correct? So here also you have your tool thrust load, you have your tool RPM. So what will be the power? P equal to F into V. What is linear velocity? R into omega, right? dF is the force at a small region. If I take a small region and then I am differentiating, correct? Any confusion? Now my tool is cylindrical, right? My tool is cylindrical and it is having some radius. So here I am not saying anything about shoulder or pin. This is, let's say, having some radius. And this is theta. What will be dF if dF is my force? So shear stress at the contact stress, that into area getting covered, right? Is it okay? Can anyone please respond? Otherwise, I cannot understand you are getting it or not.
Yes, sir. Yes.
Okay. So, what will be the area for a cylindrical portion? Tau contact. Will it be not like this? R d theta into dr to r into omega. Agreed?
Yes.
So, this will be tau contact into r square into omega into dr into d theta, right? So, if dq is my this amount, how can you find out the total heat is getting generated? You need to integrate it. You need to integrate over a region, right? So Q is equal to integration of dq. So this will be a double integral, right? Because there are two variables, r and theta. So how can you integrate it over which uh, domain you want to integrate it? So for theta, this will be 0 to 2 pi, is it not?
Yes, sir. Yes.
And for
And
r,
for 0 to R.
this is not 0 to r as such because we are having a shoulder and pin. So we will differentiate from RP to RS. Okay.
Yes. Yes, sir.
So pin radius to shoulder radius. And then you have this omega r square tau contact d at d theta. Okay. Now I am saying you that this is a sliding friction. So in sliding friction, tau is happen to be tau equal to mu p. Okay. This is directly proportional to the pressure. And for sticking friction, this is sigma y by root 3 according to the von Mises yield stress or shear yield stress. So can we differentiate this? So the final term it will end up with something like this: 2 by 3 pi omega mu p rs cube minus rp cube. If this is my equation, I'm just deriving or coming into this equation. Then can you tell me what will be this total heat getting generated? And one more thing, you have this RPM of 1000. So how can you find out this omega value? Are you familiar with this? Omega equal to 2 pi n by 60? Hmm?
Yes, sir. Yes.
This is the
2 by
angular
n by 60.
velocity. Omega equal to 2 pi n by 60. So I'm not getting into the finding out the value. Just tell me, have you got the concept or not? Yes or no? If you got the concept, then you can afterwards any kind of numerical similar to this you can solve. Have you got the idea or the funda? Huh.
Sir,
Who
above
wants to
the
join now?
tau is equals to sigma y divided by root 3.
Sorry.
Sir, this problem in this problem
Mm-hmm.
where the dq is equals to sigma y by root 3.
So
Well,
I am saying that you need to assume sliding friction. So if you are assuming sliding friction, tau is equal to mu p. This is directly proportional to the pressure. This is my contact shear stress. When does this sticking and sliding friction happen? Sticking is basically this is completely reaching at shear yield stress, and this is the highest value of that contact shear. So you need to consider a tau as mu p, not the sigma y by root 3.
okay, sir.
Okay?
Sir, in
Yep.
this equation,
Mm-hmm.
pressure is given in MPa,
Mm-hmm.
megapascal,
Mm-hmm.
and the diameters are given in millimeter.
Mm-hmm.
So diameters has to be converted into meter, I think.
Megapascal is Newton per mm square.
Yes. Yes, that way also we can put, or we can put like 10 to the power 6 Newton per meters.
In terms
Okay,
of
the
unit,
result will same.
whatever
Okay,
you
sir.
are comfortable with.
Yes.
Okay? Should we stop here?
Okay, sir. Thank you.
Thank you.
Thank you very much.
Bye bye.